Hi everyone, my name's Craig, and today I've got with me Justin. We've both got a shared interest in autonomous RC cars, and for myself, I'll tell you more about this later. I've got an RC car here, which has got a LiDAR, Raspberry Pi, Wi-Fi, and some power, and we'll get more into the details of this later. But for now, I'd like to introduce you to Justin. Over to you, Justin.
Hi, yeah, I'm Justin. I'm a software developer and a recent robotics hobbyist. Um, I've also recently built an autonomous RC car and done some hardware along with that. I'm just getting started in this space and excited to continue.
Brilliant, thanks for the intro, Justin. So you've already built your car and you've competed with it. So can you tell me more about that?
Sure, yeah. The competition was pretty exciting because um, I initially knew that I was going in solo as a solo competitor, and many of these other teams that I would be competing against are universities. It was like 5 or more people, each assigned to different parts. Um, and I kind of knew that going in, but I figured that naively that it would be not too big of a challenge to handle by myself. And that really was the hardest part, was managing the car and updating code and doing all this stuff that's like super crunch time, like it right in the moment. And a big part of it is resetting the car whenever it crashes, or picking the car back up, or fixing the track. And by yourself, that's pretty difficult. But luckily, everybody was super kind and helped me along with that, like fixing the track and getting the car ready and stuff like that.
Oh, that's cool. So it's really great that people have jumped in like that to help out. In terms of debugging and everything, I really know what you mean. When you're under pressure and you're on your own, it can be quite hard. However, if you've got a bit of a team around you, then you can bounce ideas off each other and you can come up with something that you wouldn't have necessarily thought about on your own. And in particular, if you've got a diverse team, then that can really help as well in the heat of the moment. Um, can you tell us a bit more about your car, please?
Sure. The league that I competed in is called F110th. Now it's called Robo Racer. They just renamed. But typically, those cars are a Jetson main computer, a Hakuyo LiDAR, which is a really expensive, like $3,000+ LiDAR, and some other components like a VESC for speed controller and stuff like that. And when I first started this, or deciding on competing, I did not have the same budget as the universities that can easily build one of those cars. So I figured I would build my own much cheaper if I could, and base it around the Raspberry Pi, because I was familiar with that and it's pretty cheap and easy to get. And that's kind of what led me to develop a PCB that I call the mouse board, um, that is a Raspberry Pi hat that sits on top of the Raspberry Pi and just connects pretty much any car, any RC car, and converts it into like an autonomous platform for racing or any other robotics needs.
Oh, brilliant. Thanks, Justin. So you sent me one of your mouse boards, which I was really grateful for. That helped me with my own autonomous vehicle. So yeah, I really appreciate that. Um, what was it that sort of led you to make the pie hats?
First, when I started the project, I started directly. Well, the most complicated part of the build is just getting all the sensors and controls like steering and throttle to communicate with your main computer. First, I just directly wired them into the Raspberry Pi's GPIO header, the 20-pin header that the hats connect to. But those were just directly wired at first, and I got somewhat success out of that and was able to drive the car and stuff. But I quickly realized that having a microcontroller as like a middleman between the sensors and controls and the Raspberry Pi is probably the best way to go. It just simplifies the whole implementation, and it makes it a little bit more robust, and allows like the microcontroller to handle the uh, kind of mundane tasks that would normally eat up CPU time, which is really valuable on the Raspberry Pi.
Have you got your car there? Can we take a look? Maybe
Yeah,
you can
here,
show it to the camera.
sure. Yeah, here is the car that I have. It's a really cheap, simple build, and you can see the Raspberry Pi there, and then the mouse board sitting on top. And you can see there's only three connectors coming out of it. So there's the steering servo, the throttle and power to the board, and then underneath this like white cable is the connector for the LiDAR. So it's super simple, just sits right on top of the Raspberry Pi, connects steering, throttle, LiDAR, and an optional like external IMU. And then that's it. That's all you need to convert a RC car like off the shelf into a autonomous racing platform.
So what's the microcontroller that you have on there?
So it started out as a Teensy 3.0, which is a fairly common microcontroller that you can program with the typical like Arduino libraries and IDE. And eventually I moved to the ESP32 just because it was simple to design the PCB around that. Sits right on there. It's cheap and really common, and also is regularly supported by the Arduino IDE and community. And you can pretty much write any Arduino code and make it work on the ESP32.
There's definitely good support for the ESP32s, although I haven't used them myself. I do know through the community. I've used a different ESP, the ESP8266. That was used on a kind of solar power monitoring system that I made. I haven't touched that project for a while, actually. I should get back to it. Um, so for my attempts when I originally had the Pi, I had this little servo hat, which is something a bit similar to what you're trying to do with the mouse board. But I've got to say the mouse board does it quite a lot better, because the servo hat, what it does basically, you can communicate with it over I2C bus, and you can send commands to each of these servo outputs. So I think you can control something like 16 servos from this thing, and you use one for the steering and one for the throttle. And it's pretty kind of essential really to do something like that, because the alternative is to try to control the servo directly from the Pi, which you can't really do adequately. So it's really important to have some kind of hardware to control the PWM that the servos read from. Otherwise, you're not really going to have very good control on the steering and the servo. Um, so to be honest, I still have a bit of a problem with this one, because even though you don't have to control the pulses for the servo so accurately anymore, because now this board does it, but you still have to have an update loop to send the I2C messages and update the position that you want for the servo to have. So it's still not ideal, but the mouse board is definitely a big improvement on that. So what were some of the challenges that you had with the board design when you wanted to create the mouse board?
So as a software engineer, I don't know anything about PCB design. I like know a little bit about electrical engineering just from like tinkering with Arduinos and as a kid and growing up around electronics. But I would not call myself an electrical engineer. And the hardest part was just learning KiCad, which is the PCB design software, and then picking components because like the electronics world, like there's like 100 different components that all do the same thing and that have different prices and different availabilities, and it's like finding the components and like which components go together well with other components. That's the real big nightmare of it all. And eventually you just kind of have to like, okay, I'm going to use this part, and then that kind of just justifies your design around the rest of the board. Other than that, the routing for the PCB, like once you have your schematic done and then you start actually drawing the traces on the board, that part is really satisfying. It's like pretty relaxing, just connecting lines and filling in shapes.
Yeah, okay. So I remember, I did a little bit that a long time ago, and there's this kind of magic auto root button, and I'm sure it's still there, and it just joins everything up, and then you look at it and you go, I'm going to change all that now. Yeah. So how did you find the auto root? Is it improved any?
I tried that at first and it was all right, but I think just doing it myself, which is generally the way that I like to approach things, is like try to learn how to do it myself first. And then if I give up, then try the auto route or whatever the equivalent in that situation is. Um, but yeah, no, the routing it myself was fine, mainly because the schematic was pretty simple.
Yeah, cool. Okay. Um, so then after you'd been to the race and you've used the mouse board, was there any sort of problems or hiccups that you might want to address in the future?
Right. Yeah. So there's a couple things that I would definitely change on a second version of the board. Mainly the ESP32 that I was using, it doesn't have a very accurate internal oscillator, internal clock. So getting microsecond precision timestamps or just synchronizing timestamps between the host computer is it tends to drift over time because of that fairly inaccurate internal oscillator. So what most people do and what I will do in another board would be to add an external oscillator to make the timing on the ESP32 a lot more accurate and allow synchronization between timestamps between the ESP32 and then the host computer. And this is particularly important because of IMU data or just like pretty much any data, sensor data that you get, like having an accurate timestamp or of when the data actually happened is pretty important for robotics, especially robotics at speed.
Yeah, definitely any kind of timing jitter or delay in delivering that sensor data can vary. So really important that when you're making the decisions about what to do, that you know actually when that sensor data was captured. So yeah, it's a very
Right.
valid point.
And then some other things I would change would be adding onboard IMU instead of relying on an external IMU. Because right now the mouse board just has extra I2C connectors for an external IMU. But having an onboard IMU would be a lot nicer, and it just removes one extra thing you need to mount on your car whenever you build it. Another thing would be adding a USB connector for programming and potentially data out if you didn't want to use the 20 pin header. Right now, the programming is just through a GPIO header that you have to manually connect like a USB to serial interface for to program it. But obviously you're not going to be programming the ESP32 very often because that code is pretty simple and doesn't really need to change very much. Most of the code that changes would be in the vehicle implementation on your host computer. Improved power circuitry would probably be another thing that I would improve. The current mouse board, in the pursuit of keeping it really simple and minimizing connectors to it as possible. I had to rely on the ESC providing the 5-volt supply to power the mouse board and the servos and all of that. And a lot of times the voltage supply from an ESC is not super precise or clean or exactly 5 volts, which the Raspberry Pi really doesn't like. Raspberry Pi really likes 5 volts. So what I would do is add extra power circuitry so that you can just hook your battery directly to the mouse board, any voltage, and then get the clean 5 volts for your servo, Raspberry Pi, sensors, whatever.
Right, okay, so some kind of regulator or something like that on the mouse board to protect it and give it a bit more of a stable supply.
Right. Yeah. DC to DC buck converter or something like that.
Yeah, okay, all right. So funny you should mention, I have one of those in my vehicle as well, and I've had power problems, and in the future iterations of my vehicle, I'll also be addressing that. So it'll be really interesting to see, yeah, what you come up with, and if I can also make use of that.
Yeah, that's a huge problem, but I hope to keep future versions of the mouse board just as simple, maybe just one more extra connector for the battery.
Yeah, okay. So shall I tell you a bit more about my vehicle then, and how I went about it? Because you've taken quite a different approach with your race car. You basically have done all the software yourself, right?
Yeah. So coming from a non-robotics background, I didn't use ROS at all for my car, which tends to be the standard for robotics these days. And yeah, so we went completely different routes.
Yeah, right. So yeah, and the way we first met is I saw your LinkedIn post, which was I'll definitely call it viral. It went kind of crazy because it was quite amazing. I think what you'd achieved, just writing your own software and not using anything off the shelf. Yeah, the algorithms, the visualization looked fantastic. So yeah, really super. So yeah, as you mentioned, I went much more off the shelf. So I've been working in the robotics space for a while, mainly on bespoke industrial robots, things for moving stuff around in factories and warehouses and so on. Um, and all of our software back then was, to be honest, written bespoke as well. So all of that was custom made. Back then, the ROS ecosystem, packages, and all of that was not really all that stable. There was a lot of change and also a lot of bugs. Um, so we didn't really take advantage of it. As the years have progressed, though, ROS has really improved a lot in terms of the sort of diversity of the packages, the quality of the algorithms, and uh, the software stability as well is all much better than it was. Um, and there's some really great packages that you can use for this type of scenario. So, for example, from there's a package called Nav2, which is really widely used and well supported. Um, and by the same author, there's the Slam Toolbox as well. So both of these will get you up and going, making maps pretty quickly. And then on top of that, you can then go and make routes. You can play around with the different algorithms that's available depending on your type of vehicle. So the type of vehicle that we've got, is obviously a car, which has got a different motion model than, for example, a tricycle, omnidirectional, or differential drive. But you can, pick and choose from the different algorithms to suit your particular use case, which I liked. A lot of people are using differential drive, so that is really well supported. And the Ackerman kind of car style motion model is a little bit off the beaten path. So it has been a little more difficult to find support for that, but nonetheless, it's been really good. So I did quickly show the vehicle before, but we'll just show it again. So basically, there's only really one sensor on the car, which is the LiDAR. That is used for doing the slam, and also I've got an algorithm there which I use for the odometry as well. If I open it up, and pardon the mess and jumble of wires, so in here we've got the Raspberry Pi 4 with your Pi hat on top, and there's one pin which is lifted up here, if you can just see, that's the power pin, because my ESC provides 6 volts rather than 5. So my Pi was a little unhappy for a while until I realised what was happening. Basically, it's being fed 6 volts. And then in there, somewhere buried, you'll be able to see there's the regular LiPo 2S battery. And then for the power, I've got one of these buck converters. Conveniently, it gives you a little readout of the voltage. But basically, all that's doing is converting down to 5 volts, which then can go into the Pi on its usual USB-C. Just because the power is a little unstable, I've got also a power bank on here, which gives me a secondary 5 volt supply, and I use that mainly for this Wi-Fi box. It's not connected at the moment, plugs into the Raspberry Pi with the Ethernet cable, and then that means I've got a much better Wi-Fi signal than what the Raspberry Pi can provide by itself. Basically means the vehicle has got its own little hotspot that I connect to, rather than the Pi connecting to a hotspot that is in the house or the office or whatever. So that's a quick run through of the hardware. In terms of the software, I'll just put this down. So as I mentioned, I'm using ROS. There's a lot of different flavors of ROS. There's 2 mainstream branches. There's ROS 1, which is just about gone end of life, I think it has now. And then there's ROS 2, and there's been many iterations of that. And I'm using the latest version, which works on the Pi 4 and also the Pi 5, which is called ROS 2 Jazzy, and that works with the Ubuntu Noble, which is the 2404 LTS. The software stack is basically made from a custom driver, which I wrote to work with your board, and we can go into a little bit of that, which basically receives it sends the servo signal and the throttle signal, and the driver converts a speed and steering message into the throttle and steering, so not very tricky. and all of that is developed is coming from the nav2 and slam2 toolbox software that I mentioned earlier. So what you would do is basically turn the car on, start all the software up, and then you can drive it around with a little GUI, which is called a mouse teleop. So it's quite. I'm not sure how you do your mapping, Justin, but with mine, basically there's a keyboard teleop, there's a mouse teleop. They basically do the same thing, which is allow you to directly demand throttle and steering values. So by driving the car around kind of manually, you can then generate um, collect all of the LiDAR data, which then is used to develop the map, which then you can basically save that and then use it later on for the localization. So as soon as you've got that, you can then get rid of the teleop tools, the keyboard or the mouse, whichever you're using, and then use a tool called RViz, and there are others, which basically gives you the view of the map, and you can tell the car where to go, and then you can just turn on various displays so you can see the particular route it's selected. You can put the obstacles in the way and see that as well. You can see everything that's in the map, and you can see the route dynamically update as the vehicle progresses or as you put obstacles in the way. So I mentioned I made a custom driver for your board. So what this did was using your SDK, which is basically your header file and C++ implementation, which is doing the serial port comms. All that the ROS2 node really is doing is receiving certain messages, so it subscribes to those messages, and when they come in from either the teleop or from the controller, which is part of nav2, then it will convert those messages from something like a meters per second velocity and turn that into a servo command, which is it's the pulse signal between 1000 and 2000, with the center being 1500. And I wrote a few parameters around that so we can scale it. And in the early days, that was really useful because I didn't want my car zooming into the distance once the planner decided it can go at 1 meter per second or whatever. So that was really useful to back it off. And similarly for the steering, every car's different, so where the end stops are, for the left lock and right lock. So that helped me to tune that. I've got to say the car doesn't drive great because I haven't spent that much time tuning it, and it was never really intended for racing. It's more of I built it, I should have said at the beginning, main reason for building it was to basically learn and get familiar. I do know a lot of the ROS2 ecosystem, but it's not really until you put things into practice that things really click into place. So the car has been really good sort of learning platform for me, and definitely I've picked up a lot along the way.
That's awesome. I'm glad to see that the mouse board is working for you and at least simplifying some of the electronics, the hardware part of the build, which for me was the most challenging and probably the most annoying, because I think that's a pretty big barrier for a lot of people coming into robotics, or at least like outsiders like I was, where like, oh, I want to see this car drive by itself. Like you have to like do all this setup and hardware, and like you have to have so many different disciplines to even get that far to start writing code to do autonomous stuff. But it's good to see that like it did help a little bit with the setup hardware wise.
Yeah, definitely you've done a lot of the hard work for me in terms of the electronics. Um, I would definitely agree though that robotics is a multi-discipline kind of skill. So it doesn't matter if you're making cars, arms, or anything else. It really helps to not only know your discipline, if that's software, but also some electronics and mechanical as well. And as we both go through our sort of robotics careers, I'm sure that we'll pick up more and more as we go along the way.
Right.
So in terms of the electronics, so recently I've upgraded, or I've attempted anyway, to go onto the Pi 5. So going and updating the software was relatively straightforward. I guess I made a few mistakes along the way, missing dependencies and things like that I forgot to install. But probably all in all, it took an hour to upgrade all of the software. But then after that, I have run into a few issues. So mainly that the Pi 5 does demand quite a bit more power. So my power setup that I showed you a minute ago, it's not really sufficient. So I need to think about how I'm going to do that. I could kind of scale up what I've already got. So that little power bank, I could just get a bigger one. Um, but really, I'm going to take this as an opportunity now to have a look at the setup and see if I can simplify it and make it a bit tidier. Now that I've gone through a bit of the pain and found out what some of the problems are. Um, so I'm looking forward to that. Just today I was looking at a kind of a UPS hat that you can get for your Pi. And this allows you to connect various sort of lithium cells, you know, the big round ones. They look like a jumbo AA battery. Um, and they're really not meant for this type of application, but they're meant to basically keep your power for the Pi on if there might be a power cut, that kind of thing. So you can keep, I don't know, monitoring whatever it is, maybe using it for a burglar alarm, who knows? Or maybe it's some kind of weather station and it's powered from a solar panel. It's really meant for that kind of situation, but from looking at the electronics, I believe that I can replace those round lithium cells with a regular 2S or 3S battery pack that you can put in a car, and that means I can ditch the USB power bank. We don't need that anymore, and I should be able to power everything from one unit, which would be really nice. It also will give you a bit of information as well, so it'll tell you, for example, the voltage, the current, and your remaining charge, which is always nice to know. And then the last issue I've had most recently is I tried to get your mouse board working on the Pi 5, and you did warn me that this might be a problem, and you were absolutely right. So looking in the documentation, the different things you have to do in the Pi 4 to get the serial ports working, that's all changed. The device tree overlays, that's all changed. So I haven't been able to get it working yet. The mouse board's using two serial ports, and the one that I use, because I'm not using the same LiDAR as you, which is the one for the all of the commands, that's the one which is not working. I'll keep poking at that. I'm sure it will be possible, but mainly what they've done is they've moved one of the serial ports from the header to a separate connector, and so everything I think is going to that. So I need to figure out how to use the different serial port instead, so that it will still come through to your board.
Right. I think in the second version, having just a USB port in addition to the UART through the GPIO connector would be nice in this case, because then instead of having to rely on that secondary serial port for control and sensor data, you could just straight up connect a USB-C connector from the mouse board hat to one of the Raspberry Pi's USB ports and just use that as the communication instead.
Yeah, that sounds viable. And one of the nice things about USB is that you don't need to have one physical interface for each logical interface, if I can say that. So what I mean is you could use the one USB port to expose multiple USB devices on your hat.
And regarding your power issues, so I've actually designed a second board, not intended for use with the Raspberry Pi, mainly for larger autonomous platforms, which I ended up starting to build after that competition. I have it behind me. It's a lot bigger. I can try to grab it.
Yeah, please grab it.
So this thing does not use the Raspberry Pi. This thing uses like a Intel mini PC. But this board has a lot of the improvements that I wanted to implement with the second Raspberry Pi version, such as the USB-C connector for data and communication, as well as a huge set of power components that take a 4S battery voltage and provide a clean 12 volts for LiDAR or computer, and a clean 8 volts for a beefy servo for steering. And this one also has the onboard IMU, which simplifies the mounting and external hardware a lot.
Yeah, so that's all on that PCB there, and that looks
Yep.
like another ESP32 as well.
And the code is pretty much identical to the Raspberry Pi one. It's interchangeable. It even has the same two LEDs for whatever you define, like user-defined status. Um, so yeah, the goal is to have two different boards that do that do one for the Raspberry Pi and one for like larger platforms, like a actual mini computer or a bigger lidar or something like that. Like, and I think I want to keep it that way and use both boards in the development of both to improve each other.
Yeah, that's a great idea. That gives people flexibility then, because I think you wanting to sort of share this project, so that it gives people the ability to use the Pi Hat version if that's what they've got, or if they got something else, they can use I guess the standalone one.
Yeah, and the project is all open source, so the schematics and code and everything is on my GitHub. I never intended to keep it all private. I want everybody, like the goal is to get more people involved in this hobby or this robotics journey, I guess. Make it easier, lower the barrier to entry in terms of hardware skill and just cost in general.
Yeah, definitely. Yeah, I think that's a really great goal to have, and it I guess repays that kind of help that you got when you went to do the race. You know, people were mucking in, helping you, so it's your
Yeah,
way of giving back, I guess, and sharing and encouraging others to join in.
yeah, yeah. It's been a really fun, really cool, super uh, enlightening journey.
Oh, so Justin, yeah, there's two other things I want to mention. So one of the problems I have with my car is that because I've only got the one sensor, the lidar. That's used for the slam and it's also used for the odometry, and that means that the odometry is not being updated very often. It's only like 5 times a second, 5 hertz. But there's another sensor that I plan on integrating onto my car, which is an optical flow. Um, Traditionally, these have been used pretty broadly in drones, so you can have this pointing down at the floor on your drone, and as it flies through the sky, it will continually check the difference of the image. It's got a tiny camera on there, and it looks at how the image is changing to be able to calculate its velocity. Um, so this is something I plan to include into my car. I did do a bit of validation on it a long time ago, but that was before I was so experienced with ROS. So I plan to write a ROS driver for that. Um, I'll open source that. I'm going to match you. You're making your project open source. I'll do the same. Um, and I'll share the results as well. So hopefully that should mean that my odometry will start coming in much more frequently. That might give me a few issues now because a lot of the processing, which is only happening every sort of 100 milliseconds, would need to probably be repeated much more frequently. But hopefully the Pi 5 will help with that. Um, and then I mentioned the control of my car is pretty poor. So there's a number of problems really. One is with the model predictive control, which I haven't really bothered to tune, which is the control algorithm I'm using for the Ackermann motion model. And then the other one is the conversion of the speed from a meters per second value into a throttle value, and likewise for the steering. So I plan to use some reinforcement learning, basically gather some data from the car. Perhaps I'll do some simulation as well. But what I hope to be able to do is certainly replace that last one with a reinforcement learning algorithm that will give me a much better control. And there's numerous examples of this I've seen on YouTube, mainly mainly gaming. Actually, people have got their cars to drift in some of these car racing games and things like that. But I guess I've been inspired by that, so hopefully I can improve the control of my car by having a model which is going to much more accurately be able to control based on this model, what the actual car does. So yeah, I'll let you know how that goes. That'll be interesting. I haven't done any machine learning before, reinforcement learning, so that's going to be quite new.
Yeah, that's super cool. The whole optical sensor idea is kind of fascinating because it kind of reminds me of like a computer mouse, like just a sensor looking down straight at the ground, tracking X and Y movement. It's super, super interesting. And I'd imagine you get pretty good, pretty accurate results for that too. That odometry problem is a really hard one to solve, and it's not a easy thing to solve because generally that means like hacking together some hardware changes to your actual vehicle regarding like putting an actual encoder on a wheel or um, something like that. um, One way that I've been able to get around it is through my ESC actually. So I started with drones a really long time ago, like building custom like racing drones and stuff like that. And the drone ESCs, they have what it's called. Well, they just have telemetry back to the flight controller, so the flight controller knows how fast each propeller is spinning at any moment. And that same technology or the ESC firmware, you can find that for RC car ESCs or bigger ESCs. And I've kind of taken advantage of that with my mouse board and with the ESC that I'm using. I can get ERPM, so electrical RPM of the motor, back to the mouse board, and that's how I'm doing odometry. It's not super accurate, but it is accurate enough to have like closed loop control on velocity.
Yeah, okay, yeah, that's a really great way to do it. Unfortunately, my ESC and the motor don't provide that input, but I would definitely use it if it did. So yeah, that's a great one. And your analogy with the optical sensor, yeah, you're bang on. It's the same technology that you have in a computer mouse, basically. The one thing that's missing from it, and just it's exact same with your mouse, is it doesn't do any rotation. So probably would need two of them on the car, uh, side by side, so that when the car rotates, then I'll basically see the difference in the forward velocities of the two different sensors. Something like that. It's a work in progress.
Super cool. I'm excited to hear how it goes.
Yeah, and yeah, it'll be interesting to see as well how the results compare with an IMU. So you're going the IMU route. I'm going to try the optical flow, and yeah, I guess we'll compare notes.
Yeah, yeah, super cool. I'd imagine there'd be less drift too, because with an IMU, you end up with a lot of drift if you want to track, or if your goal is to track like absolute orientation. You can sort of correct it with a compass, like an IMU that has a magnetic compass inside, but even that will not be perfect. But I imagine your approach would be pretty much spot on all the time.
Yeah, theoretically, so there'll be a bit of calibration for its position on the vehicle, but after that there shouldn't be any calibration needed really, and that's one drawback with the IMUs, isn't it? Typically they need to have some kind of calibration performed from time to time. So, okay, shall we wrap it up there?
Yeah, sounds good.
Okay, well it's been great, Justin. Great chatting with you again, Justin.
Yeah, likewise. Great chatting with you, Craig.
We'll have to have a catch up soon when we've both made a bit of progress on our vehicles. So I look forward to chatting with you again.
Yeah, absolutely. Thanks, Craig.